In this video, we're going to take a look at the ideal gas law. It's one of the final gas relationships for this unit. After this, we're going to be able to do stoichiometry problems because now what we're doing is we're taking a look at a formula that incorporates essentially all the variables we've discussed plus the mole. So before you do attempt this note, I do recommend you watch the Ideal Gas Law Preview the Material video with Tyler Dewitt over here. Does a great job at explaining all the different variables and what the formula is all about. So it gives you a bit of a preview. And if you want to leave this to the end to watch as a summary, you can do that as well. There's a warm-up question you can try out here that goes over the concepts we've seen before. The answer key is over here for you to take a look at it. But do make sure you understand the previous concepts before you go on to the most recent formula that we're doing now. The first few slides, we covered just a brief review of ideal gases. So remember, we saw the kinetic molecular theory. We saw that it explains the behavior of gases that are considered ideal gases. They're hypothetical gases, so they don't really exist, but we can still use these ideas to explain behavior of real gases because they're pretty close in terms of their behavior, in terms of what happens. So remember that these were the main assumptions. So ideal gases are hypothetical gases that travel in straight lines. They have negligible volume for the particles, so they're called point masses. They don't have any attraction or repulsion to each other, towards each other. They experience elastic collisions, so they don't lose energy. The kinetic energy is preserved when they collide with each other. And they have energy that's directly proportional to temperature. So as you increase one, you increase the other. If you double one, you double the other. And we use these assumptions for ideal gases because it makes the math easier for us when we're trying to support observations with calculations and we're trying to explain those observations. Essentially, assuming this hypothetical gas works as long as you have situations where gases can behave as gases. If you have pressures that are too high and too low, then the real gases are going to sort of start to liquefy, and they're not really going to follow these assumptions anymore. So the ideal gas assumptions do work as long as we're not in these very, very high pressure, low temperature situations. And for the most part in grade 11, you're going to see situations where the assumptions do work. So remember, we saw those were the assumptions of ideal gases. Now, real gases, in reality, molecules of real gases do have a volume of their own, but it's so tiny we can still go with the ideal gas assumption that they don't have a volume. They actually do have an attraction towards each other, but again, it's such a small attraction that we don't need to consider them when we're doing our calculations and explaining our observations. And they don't necessarily move in straight lines, real gases. They do something called Brownian motion, which is very similar to moving in straight lines, but it's a little bit different. But still, because it's a little bit different, or because it's very similar, we can just assume that they travel in straight lines. And the collisions, in reality, they're not completely elastic. They're actually inelastic collisions, but it's such a small amount of energy that's lost in those collisions that we can pretend they're elastic. So our ideal gas law assumptions will work for real gases because all these things are super, super, super small when it comes to real gases anyways. So this final table here just summarizes ideal gases and real gases. Do take a quick look at it so you understand the difference between ideal and real. A real gas are the gases that actually exist. Ideal are the assumptions that we make just to make our observations or explanations of observations easier and our calculations easier because we're able to make these assumptions to simplify things a little bit. So we've seen a bunch of formulas in this unit. We saw all these different laws over here, including another law called Dalton's law of partial pressure. But what we're going to do now is we're going to take a look at our last law, which is called the ideal gas law. PV is equal to nRT. And a way you can think of it is combining all these different laws together. If you take Boyle's law, which looks at the relationship between pressure and volume, Charles' law between volume and temperature, Gay-Lussac's law between pressure and temperature, and Avogadro's law between volume and number of moles, if we put them all together, we get PV is equal to nRT. We have a pressure, our volume, our temperature, and the number of moles all in one. In order to create this formula, scientists had discovered a constant to basically join all the different variables together. And that's called the gas law constant. So this will always be the same, 8.314 kPa times liters per moles times Kelvin. So those are the units for the R constant. Do make sure you know them because we're going to try to cancel units out in our calculations as well. Now, I did say the R value, the R constant is going to be the same all the time. In terms of the number itself may change depending on your units. So there's actually a table that you'll see in just a little bit, this table over here, values of the universal gas constant. It gives you what the value is depending on what units of pressure that you're using. So for example, here we're using ATM. These are the units over here. So we have liters, ATM, Kelvin, mole. So depending on the units of pressure you have, you might have to use a different R value. We, for the most part, will use the R value that's 8.314 kPa, liters, moles, Kelvin, and that's because our pressure values should be in kPa. If your pressure values are not in kPa when you're using your PV is equal to nRT formula, then what you want to do is you want to convert those values into kPa. Otherwise, you won't have proper unit cancellation and it won't work out the way you expect. So let's go ahead and take a look at our formula. It's PV is equal to nRT. P is the pressure, V is the volume, and N is our number of moles. We have our gas constant, which is over here, 8.314 kPa, liters, mole, Kelvin. And we also have our temperature, which is in Kelvin. As you can see, we have Kelvin in our R constant. Our volume has to be in liters. We have liters in our R constant. Our pressure has to be in kPa if we're using this 8.314 because our kPa is in our gas constant over there. Our moles, well, that's simply in moles because, well, it's moles. And so you have that in your R value as well. So there's moles right there. So this is PV is equal to nRT. And essentially you can manipulate this equation to solve for many things. You can find pressure if you have your moles, R, T, and V. You can find your moles if you have PV and RT. You can find your temperature if you have PV and NR. So you can manipulate this to find whatever you're looking for a given circumstance for certain gases. So remember, convert your pressure to kPa and to convert your volume to liters and your temperatures to Kelvin in order to use this formula as needed. So we'll do a few examples together. Before we do that, though, I just want to go and point out a couple things about the gas law unit. So if we look at data tables, we have the ideal gas constant here, along with the units as well. So you have that you have that piece of information there. So, if you forget the units, you can come back and take a look at it over here. And we also have our conversions for pressures. So if you have a unit that's a pressure that's not in kPa, you can convert to kPa to use your R constant. And then you can also see your STP and SATP are provided to you over here as well, just in case questions provide you with a condition of STP or SATP. Let's go ahead and do some fill in the blanks and some practice problems. So again, here we simply have our comparison of our real gases and ideal gases, and we can see all the different formulas that we learned. And what we're doing is we're taking all those different formulas and we're putting them into one for our PV is equal to nRT. And to be able to connect all those different variables, you have to use a gas constant. And the main gas constant we'll be using is this, providing that our volume is in liters, our pressure is in kPa, and our temperature is in Kelvin. And it's 8.314. So these are just some little tips to use the ideal gas equation correctly. And here we go. Let's do a few basic PV is equal to nRT problems. So we have the Goodyear blimp has a volume of 2.5 times 10 to the power of 7 liters and usually operates with a gas at a temperature of 12 degrees Celsius and a pressure of 112 kPa. What mass of helium does a blimp contain? So let's go ahead and first of all write out some information. We have volume is 2.5 times 10 to the power of 7 liters. We have our temperature provided to us as well. Our temperature is 12 degrees Celsius, but don't forget you do need to convert that to Kelvin if you want to use these. And we've been converting to Kelvin all along for our other formulas as well. But plus 273.15, and we get 285.15 Kelvin. We also have our pressure, and luckily our pressure in this case is in kPa, so 112 kilopascals. And what we're looking for is the mass. Now remember, mass is equal to moles times molar mass. So we need to find moles and molar mass. Now, our molar mass we already have. Molar mass is for helium. I believe it's helium. Is that correct? Yes, helium. It's 4.00 grams per mole. So we're good with that. What we need, though, is our mole value to plug that in there. Now, if we're looking for a mole value, we have volume, we have temperature, and we have pressure. We know that we can use our PV is equal to nRT. Don't forget that R is equal to 8.314. We'll put the units after. I'm just writing that down right now, and then we'll show you the units in the actual formula. So since we have all these things, pressure, volume, R, and T, we can rearrange this equation to get that the number of moles is equal to PV over RT. And we can plug our information in. So we can do 112 kPa multiplied by our volume, 2.5 times 10 to the power of 7 liters, divided by our 8.314. And if you look at the units, it's kPa liters per mole Kelvin. So kPa liters, that's multiplied there, per mole multiplied by Kelvin there. And then times our temperature, which is 285.15 Kelvin. And we can go ahead and cancel a bunch of stuff out. So we'll cancel out our volume, liters out, our kPa out, our Kelvin gone. And what's left over? Moles. So let's go ahead and plug this into our calculator and see what we get. So we get 112 times 2.5 times 10 to the power of 7 divided by 8.314 gas constant divided by 285.15. And we get really a large number of moles here, and that's okay because we're filling out a blimp, so it makes sense. Moles. And just verify, so I'm pretty sure we're on the right track here. 112 times 2.5 times 10 to the power of 7 liters divided by 8.314 divided by 285.15. And that's right, that works out. And so now all we have to do is take our number of moles and put them into our mass formula. So M is equal to our number of moles of helium times our molar mass. Cancel out moles, and we're left with grams. Grams. I'm going to write this as a scientific notation, but rounded to, it looks like 2 sig figs. So we're going to have 4.7 times 10 to the power of, so we'll move it 1, 2, 3, 4, 5, 6 times 10 to the power of 6 grams. So 4.7 times 10 to the power of 6 grams, and you can write your therefore statement. So therefore, the mass of helium is approximately 4.7 times 10 to the power of 6 grams. That's how much would be in the Goodyear blimp. And let's go verify our answers just to make sure we're on the right track. And that's right. It looks like we're on the right track there. And this makes sense. I mean, yes, it's a large number, right? You have a very large number there. You're in the millions, but that's no big deal because you have a blimp. So you have a lot of gas in there filling in that blimp. And so that's our final answer. For the mass of helium using PV is equal to nRT. We knew we had to use it because we had to find the number of moles. And the only formula that we know that has the number of moles and all these other things related to it, so the volume, temperature, and pressure given, is that PV is equal to nRT. There are other methods you could have used. So you might, maybe think about how you could have maybe used Avogadro's law here to see how you could have done it. But this method is probably the simplest method to use because we have our PV is equal to nRT. All the variables are related. Avogadro's law would be difficult to do because you don't really know these conditions here. This is not STP or SATP, so it would have been a little bit tough to use our molar volume concept unless we knew the molar volume at these particular conditions. So we couldn't really use the molar volume in that scenario. So in the next video, we're going to do a few more basic practice problems related to the PV is equal to nRT. So you can try them out before we go to the video, and then afterwards check your answers in those videos.